neutrino and antineutrinos are distinct particles, while in the latter case, neutrino is its own antiparticle, and we will see later what is the main consequence of this. What is no more debated is the fact that neutrino do have masses, and the major evidence for massive neutrinos come from oscillation experiments. Oscillations are transitions in flight between neutrino flavors, and this means that the probability to observe this transition, for example, between muonic and tauonic neutrino is different from 0. This probability can be expressed as a function of neutrino masses and neutrino mixing parameters. In other words, the known neutrino flavors are a superposition of mass eigenstates with coefficients given by the neutrino mixing matrix. This matrix can be parameterized via the mixing angles theta ij and CP violation phases. One if neutrinos were Dirac particles, two more phases if neutrinos were Majorana particles. Oscillation experiments are sensible to some of these oscillation parameters, to the theta ij and to the squared mass difference between the eigenstates. The little delta is the difference between the first two eigenstates, while the big delta is the difference between the third eigenstate and the mean value of the first two. We can see from the formula of big delta that this parameter can be greater or lower than 0, identifying two different hierarchies. The normal hierarchy if the third eigenstate is the most massive one, and the inverted hierarchy if the third eigenstate is the lightest one. Unfortunately, oscillation experiments are yet not sensitive to distinguish between the two hierarchies, and what is more, they are not sensitive to the absolute scale mass. So there is a need for further experiments in order to probe this neutrino property. As far as particle physics is concerned, the kind of experiments which will probe the absolute scale mass involve beta and double beta decay. These plots show the spectrum of the tritium beta decay, and we can see that the behavior of the spectrum close to the endpoint is very different for massive, the red line, and massless, the red line, and massive, the blue line curve. The goal of beta decay experiment is exactly to reproduce the endpoint of this spectrum in order to assess the impact of the offset between massless and massive case. This offset can be parameterized through the neutrino electron mass and beta as a function of mixing angles and mass eigenstates. And here I reported the current upper limits on n beta and future expected sensitivity, for example, from Catherine experiment. This kind of experiment involving beta decay provides the broader constraint on the absolute scale mass. However, they are very powerful since they are completely model independent. But apart from beta decay, also double beta decay can occur when two electrons and two antineutrinos are produced. If neutrinos were Majorana particles, then the two antineutrinos would annihilate, and so electrons would be the only decay products. Experiments looking for neutrinoless double beta decay are sensitive to the half-life, T-half, of the isotope involved in the decay, and theoretically speaking, this can be expressed as a function of G, the phase space factor, that is easy to calculate in particle physics, M, that is the nuclear matrix element, and it is more difficult to calculate, and we will see later the impact of uncertainty on M calculation. And finally, the parameter of the absolute scale mass, that is the Majorana effective mass. Here is the formula, and I reported the current upper limits on T-alpha and expected sensitivity from future experiments. Taking into account the uncertainty on M calculation, the allowed upper limit on M beta lies between 0.2 and 0.5 eV currently. So the main problem when dealing with a neutrinoless double beta decay experiment is exactly to assess the uncertainty coming from NME calculation. But also these kind of experiments are very powerful, since if observed a non-zero value for M double beta, this will solve definitely the problem about the neutrino nature. Finally, what kind of information we can learn from cosmology? We have two different observables, the CMB power spectrum on the left and the matter power spectrum on the right. They are both sensitive to the sum of neutrino masses, because the massive neutrinos contributed to the total energy content of the universe, and so they change the expansion rate of the universe. As far as CMB is concerned, the main impact is in shifting and smearing these peaks in the power spectrum. But massive neutrinos also alters the way cosmological structure grow, because they prevent structures to collapse below a certain scale, that is the neutrino free streaming scale. In fact, we can see from the right plot that more massive neutrinos produces less power at lower scales. But massive neutrinos also modify the wiggles we can see in the right plot, and these wiggles are the matter equivalent of the peaks in the CMB spectrum. They are known as baryon acoustic oscillations. They are produced through the counteraction between gravity and radiative pressure in the primordial plasma. And obviously, massive neutrinos, because they alter the composition of the primordial plasma, also modify the amplitude and the separation of the BAO. Current limits on sigma from CMB and from BAO are reported in these two slides, and we can see that they are the tightest constraints on the absolute scale mass. However, the price to pay is that this kind of constraints are very model dependent. We are now able to discuss more in detail the kind of analysis we performed. We choose to follow a Bayesian approach in our analysis, performing a Monte Carlo Markov chains analysis. And our baseline model is the global fit to the oscillation parameters given by Forero, Tortora, and Bayer very recently. The vector of parameters is composed by the sine of two mixing angles, the two squared mass differences, the two Majorana phases, and finally, as a probe of the absolute scale mass, the total mass of neutrinos. Since oscillation experiments are not sensitive to Majorana phases and sigma, we kept this parameter to have uniform distribution, while we consider the first four parameters as Gaussian distributed around the best fit value with variance given by the semi-width of the 1 sigma range given by Forero et al. Then we build the total likelihood simply as the product of the single likelihoods. We are not considering a possible correlation between the mixing parameters. Then we add further datasets, and we add information from particle physics, in particular from the neutrinoless double beta decay experiment GERDA, from CMB through Planck, ACT, and SPT, and from BAO large-scale structures. These datasets provide further likelihoods, Gaussian likelihoods, with the parameters listed here. Few more words, however, have to be spent for GERDA, since this plot represents the different calculation, the different results from calculation of M for different nuclei model, the different colors in the dot, and for different isotopes. Please focus on the germanium case, that is our case, and we can see that the difference between the lower and higher value is about a factor of 2. We choose to take into account this uncertainty by introducing the nuisance parameter psi and marginalize over this parameter. Psi is defined as the ratio between a reference value for m and the unknown exact value. This is the expression of T alpha as a function of psi, and then we can build our likelihood of T alpha given m double beta and m psi. We choose this likelihood to be semi-Gaussian in n beta, centered in 0, and with variance got from the lower limit on T half from Gerda experiment. Psi has a flat prior spanning between the range 0.5 and 2. That is a factor of 2 respect to the reference value. We are now able to discuss the results, some of the results of our analysis. First of all, the allowed parameter ranges for oscillation data only. Notice the lower limit, physical lower limit coming from oscillation data on these three parameters, that is sigma, m beta, and m double beta. We can see that sigma is different from 0, obviously, because we are considering neutrinos to have mass. Then we can also recognize the degenerate region, that is the region in which the two hierarchies are not distinguishable. We can see that a future particle physics experiment, in order to distinguish between the two hierarchies, has to explore the region below 0.1 eV for m beta here, and for m double beta here.
Sorry, which is the difference between these three graphs in the slide?
They are simply the allowed regions, so not statistical information are encoded here, and the red part is for normal hierarchy calculation, and the blue one is for inverted hierarchy. Obviously, we cannot say anything about the two hierarchies with this analysis because we have to assume before the kind of hierarchy in order to calculate the different parameters. Maybe a Bayesian model comparison would help in this sense. These are instead the information we can learn by adding the other data sets. First of all, we can see that Gerda, that is the red plot here and the green curve below, provide the broader constraints, while the tightest constraints come from CMD plus LSS. We can see that the two-dimensional contours are closed here. Then we can also notice the shift between the two cosmological datasets. Remember that the red one is for CMB only, and CMB only provide only an upper limit on sigma, while the blue one is for the combination of CMB and large-scale structures, and this combination provides an evidence for sigma to be different from 0, and this result is reported in the other two parameters. Here we can briefly observe the impact of marginalization over psi. Remember that psi appears in the denominator of the log likelihood, so its main impact is to make the higher masses, the higher m double beta, to be more probable than the other one. The comparison is between two models, one with psi treated as a free parameter, and one with psi fixed to 1. Here, psi fixed to 1 is the green one, psi free is the blue one. These are the results by adding the further datasets. Provided the constraints on sigma are correct, are these ones. These are the information we can learn on m double beta and m beta. That is, these two parameters lie between the range 0 and 0.2 eV. Remember that the expected sensitivity from Catherine and from double beta experiments are 0.2 eV and 0.1 eV, so they seems to be not sufficient to efficiently explore the region for these two parameters. What is more, future experiments, in order to distinguish between the two hierarchies, have to explore the region, for example, far below 1 eV, that is below 0.05 eV. This statement is also clear from the below plot that shows the 1 sigma and 2 sigma ranges for m double beta for the different data sets, and the vertical line is the expected sensitivity from future m double beta experiments. Obviously, increasing the sensitivity on sigma from cosmological datasets would help increasing the sensitivity on m beta and m double beta. For example, this is the upper limit on m double beta as a function of the upper limit on sigma. The vertical line is the current state, and we can see that lowering the upper limit by a factor of 3 would lead to m double beta lower than 0.1 at 95 confidence level. The right plot shows instead the comparison between the 2 sigma ranges for m double beta for the CMB plus LSS1A dataset for different value of the variance. The upper one is the current state. The second whiskers are for halving the variance, and the final one is reducing the variance by a factor of 10. And we can see also by eye that the impact on m double beta is to almost halve the 2 sigma range. Now it's time for conclusions. I simply listed them here, and if you have further questions, please ask me or email there. Thank you.
You, Martina? Any questions?
Only a curiosity. If I understood well, you treated psi in 2 different ways. In some graph you fixed it, and in other ones. You told that when you treat this as a 3 parameter, you use a flat distribution for it. But my question was, I can see that, of course, the impact of the exit value does not have such a big effect. My question is about its the fact that you assume a flat distribution. I mean, what is the impact of psi in the estimation of the sigma, of the final sigma? I mean, psi in some way is not parameterizing the uncertainty of the mode of the computation of the Mark experiment. Okay? But in your graph, you show that in fact the predictions are not so distributed uniformly in the you see that there are 3 values very close to each other and 1 higher value. So does the fact that you're assuming a flat distribution for it does
it comes from the consideration that the difference between higher and lower values is a factor of 2, so we choose a range broader than this factor.
But I guess that if you assume the distribution is flat, the related sigma for C is always overestimated. Does not make sense what I'm saying.
Yes.
I mean, maybe that the effect is very small. I don't know. It was only curiosity.
We didn't check for changing the distribution of psi. This is just the first step in order to consider this uncertainty. But the problem is that different nuclei models produce different values, and these are just 3 kinds of models. There are more than I guess. So maybe this is not the real case of NME total distribution.
You go to the next slide. So I didn't get honestly. I didn't get why the inverted hierarchy case the endpoint is different from normal inverted hierarchy. So it's near the block.
Because the behavior in the non-degenerate region is very different for the 2 hierarchies, and I guess the main difference comes from leaving the 2 Majorana phases to vary with respect to the normal hierarchy. This is the main difference between the 2 hierarchies, is including the variation of the two minor phases.
But generally speaking, so the cut is a physical cut.
The cut is a physical cut because it comes from oscillation data. You are assuming a certain distribution for the mixing angles and for the squared mass difference, and so the cut you obtain is exactly the cut coming from the distribution of these parameters. If you don't allow a Gaussian distribution, for example, of the squared mass difference, maybe in the case of inverted hierarchy, you can reach m double beta, or you can reach for m double beta also the zero value. The cut here is given by the Gaussian distribution of the squared mass difference.
Any other question? Okay, so let's begin again. We'll move to the next presentation. By Ivan Del Vecchio, who will tell us about tracing the symbiotic growth between black holes and galaxies.
Okay. Can you hear me? Okay. Hi everybody. Okay, I will talk about yes, evolution of black holes and galaxies from an observational point of view. I'm a PhD student at the University of Bologna, and first of all, I wish to thank the organizers for giving me the opportunity to speak here today. Okay, the outline of the talk is a few questions at the beginning to introduce what black holes really are, which kind of black holes are we talking about, and then how to see, how to detect a black hole, where we believe, and more importantly, why do we care about them. And this latter question will open the second part of the talk. It is devoted to illustrate the state of the art on black holes and galaxies today, the current open issues, and a few results from the Herschel satellite. And I will finish the talk with a short summary. So first of all, for those of you who are not familiar with black holes, from a very schematic and simple view, a black hole is a region in space-time where the escape velocity is larger than the speed of light, so that nothing can escape the gravitational potential of the black hole, so that by definition it is black, and so it is not observable in a direct way. So you can just probe its presence through indirect evidences. And in astrophysics, there are two kinds of black holes, stellar black holes and supermassive black holes. Stellar black holes represent the final stage of the evolution of very massive stars, so much more massive than the Sun. According to the stellar evolution theory, stars like 10 times the mass of our Sun evolve like red supergiant, then they explode as supernovae, and one possible remnant is a stellar black hole. But this stellar black hole is still black, so not detectable itself. So you need this black hole to be accreting gas. So what we detect from black hole is the light due to the gas that has been accreted onto the black hole. And when the gas is accreted, it gets compressed and so heated up, and so emits light. So it is an indirect evidence. And when we talk about luminosity of the black hole, we mean luminosity of the gas is accreted onto the black hole. This kind of stellar black hole can reach up to 10 to the 5 times the luminosity of our Sun. And they are typically in binary systems, for instance, accreting gas from a companion star. And somehow a scaled-up version of these stellar black holes are supermassive black holes that, as you can guess, are much more massive. Their mass can reach up to 10 billion times the mass of our Sun. And the luminosity is much higher, can reach up to 10 to the 14 times the luminosity of the Sun. And when they are accreting and they switch on, they are called also active galactic nuclei, or AGN, because they reside at the center of probably every galaxy. So when they become active, they are called AGN. So I will focus on this supermassive black hole in this talk. This is a very schematic view of the structure of supermassive black hole. So you have, of course, the black hole, which is surrounded by a sort of accretion disk of hot, inflated material that is spiralizing onto the black hole. And this black hole can be detected through optical and X-ray telescopes because it is very hot material, so very strong radiation field. This accretion disk is then surrounded by a colder structure composed by gas and dust also called torus, because it has a sort of donut-like shape which surrounds the central engine. And this emits in the infrared. So just to stress that in order to study these objects, you really need a multi-wavelength approach, because different wavelengths typically sample different spatial regions. So really, it's important to investigate from a phantomatic point of view. Assuming that the observer can see the structure in front of the line of sight, another configuration is when you see the AGN edge on, so you see it on profile, and so this cold structure hides the innermost structure, so that typically optical and X-ray telescopes do not work so well in these cases, but still infrared give a more unbiased view of these objects, roughly regardless of the configuration. And where do they live? So as I mentioned before, these supermassive black holes typically live at the center of galaxies, but there is a very, very large gap in size between the size of the galaxy and the size comparable to a massive black hole. It is a factor of 10 billionth time in size, so mind the gap. And one legitimate question could be, why do we care about black holes if they are so small compared to galaxies? And we do care because people surprisingly found interesting correlation between the mass of the black hole and the mass of the bulge. The bulge is just the inner part of the galaxy, which shows this thicker region. And there is still a factor of 10 to the 9, 10 to the 10 in size. But if you measure, at least in the nearby universe, for different galaxies, the mass of the black hole and the mass of the bulge, you see that they show a relatively tight correlation, which is this, also called Magorian correlation, which is telling us that there is some deep insight that black holes can give us about the evolution of galaxies, because it means that black holes, even if they are so small, they shape really the properties of the host galaxies. And so this is a key starting point to investigate the AGN galaxy connection also in the far universe. And so people have started also investigating different types of galaxies, different types of AGN. One way of classifying galaxies could be as a function of their star formation rate, so how much efficient is the formation of stars, so the number of stars formed per unit time, basically. And so we can distinguish from low to high values of star formation rate. This red galaxy is also called elliptical or spheroidal galaxies, which have old stars and are evolving through the cosmic time passively because they only have old stars. And a key ingredient to form stars, just to remind you, is that you need cold gas collapsed. So the gas in these galaxies is too hot to form stars. And if you go in the middle, you see normal spiral galaxies with these, I don't know if you can see them, spiral arms, which are bluer than what you can see here. They are bluer because they host young stars. And if you go to higher star formation rate, you can find galaxies also interacting with each other, which offer likely opportunities to get cold gas collapsing, and so creating and enhancing the star formation rate. So these are typically more star forming compared to isolated galaxies. And the same kind of classification can be found also for supermassive black holes. You can find supermassive black holes quite quiescent. Here, there is a galaxy hosting a black hole, but you don't see really evidence for the black hole activity. On the other hand, you see also the galaxy is completely outshined by the black hole if it is accreted enough gas to switch on and to emit jets or other kind of feedback that can also impact the structure of the whole galaxy. So that people have tried to collect all this information into a self-consistent and global picture. One of the most widely accepted is this, from Hopkins et al., the AGN stop star formation. So the correlation that we see now in the nearby universe is due to a self-regulation mechanism due by the black hole on the galaxy, in particular the AGN stopping star formation. This very quite tight picture can be summarized in 3 steps. So for this picture, you need interaction mergers between 2 or more galaxies collapsing one to the other. And this collapse generates, as I told you before, a higher star formation rate, but at the same time, part of this gas involved in these merger events and also fall into the gravitational potential on the black hole, and so trigger also black hole activity. But as soon as the black hole activity switches on, well, it can also emit large amounts of matter or radiation. This kind of feedback can also sweep away the gas of the galaxy and also keep the gas of the galaxy too hot to form new stars. And so this is one possible explanation for the presence of elliptical and red and dead galaxies in the nearby universe. so due to AGN feedback. But according to this picture, you would expect to find powerful AGN activity in interacting galaxies. But this is not the case, because recent works analyzed the morphologies of AGN host galaxies, and they saw that there is not a direct correlation between the level of distortion of morphologies and AGN activity. So basically, for different levels of distortion, you find that the fraction of galaxies hosting an AGN and not hosting an AGN is quite similar. So it is telling us that this merger scenario is not the prevalent scenario which explains the black hole galaxy coevolution. So there should be some other mechanisms responsible for triggering black holes and galaxies. And typically, there is also the reversal of the argument. So the recent works are claiming that AGN now correlates with star formation. So the more star formation, the more powerful the AGN activity. For instance, if you, in the y-axis, you see the cosmic time. You know, in astronomy, if you sample very, very distant objects, you are looking much more in the past, basically. So if you can see here the look-back time, which is the time from the Big Bang, which is also a proxy for redshift. So the higher the redshift, the more distant are we looking at. And so if you take a census of many galaxies and measure the total budget that they released due to star formation, and compare this budget with the total budget released by the same galaxies due to IGN activity, they have quite a similar shape, peaking around redshift 2, which means 10 gigayears ago, so when the universe was quite young, only 4 gigayears old, so 20% of its current age. And this means that there should be some correlation between star formation history and AGN accretion history. So the evolutionary paths are quite similar, quite parallel each other. And so this opens new door towards the understanding of AGN galaxy evolution. And especially the Herschel satellite is giving new insights, new perspectives on this field. Because the Herschel satellite, which was, because it has already gone, unfortunately, but it has worked very well for a decade, more or less. And the Herschel view of the AGN galaxy coevolution is very important because while the AGN are ubiquitous X-ray emitters, and Herschel samples the star formation rate of galaxies. So basically, you can use Herschel in the infrared plus some other X-ray telescopes with a joint view to really investigate in the best way the AGN galaxy evolution. So for the same galaxies, you can infer the properties of the AGN from X-rays, the properties of star formation from Herschel, and try to test possible scenarios between star formation rate and AGN luminosity, so basically AGN accretion rate. So you can find a positive correlation that would imply a coevolution, as well as you can find also an anti-correlation that would imply a quenching, so that AGN typically stops star formation. So we can ask ourselves, is there a correlation between AGN luminosity and star formation rate? What is really interesting is that this recent result from Rosario et al. That compare the fraction of galaxies which are detected by Herschel, which basically tells us what is the fraction of star-forming galaxies, basically, comparing this fraction between AGN hosts and inactive galaxies. And you can see that these panels are for different epochs of the universe. In different epochs, AGN host galaxies are always more star-forming compared to inactive galaxies. So this is telling us that typically AGN host galaxies are less likely to be quenched, so are less likely to have their star formation suppressed by the AGN. So in some sense, this is pushing for the coevolution between AGN and galaxies. Okay. And another interesting result is the correlation between the AGN accretion rate and the star formation rate. So how many masses in stars galaxies are forming versus how many, which is the mass of gas accreted onto the black hole. You find a nice correlation that holds for different redshifts, so for different epochs of the universe, from the present day, which is redshift 0, up to redshift 2.5, which is 10 gigayears ago, sorry. And basically, if you take a large sample of star-forming galaxies hosting an AGN, and you infer the properties of star formation from Herschel, the properties of the AGN activity from, for instance, an X-ray telescope like Chandra, and you compare these properties, you find an interesting correlation. But another interesting point is that if you compare these values for individual galaxies, you don't see any correlation. But if you beam your sample and you average in each beam, you see this kind of correlation. So how it's possible to reconcile these apparent controversial results? Well, this is explained through a variability timescales of the AGN. Basically, if you imagine that you have a galaxy that also has an AGN, but the AGN is quiescent because, for instance, it's not accreting gas at all now. So basically, this is the luminosity of the AGN as a function of time. As soon as, I don't know, a gas cloud falls into the gravitational potential of the black hole switches on a relatively short time scale. This peak is that time scale. And so in this phase where the black hole becomes an AGN, an active galactic nucleus, you would expect a correlation between star formation rate and black hole accretion rate. While in this case, you wouldn't expect any correlation just because the black hole is not accreting. In this case, the correlation is driven by the common factor that is basically the gas, the cold gas. The cold gas triggers star formation, as well as the cold gas triggers AGN activity. So basically, since it is very unlikely to pick up your objects in this phase because it is short-lasting compared to the galaxy's lifetime, for individual galaxies, it's very unlikely to see a correlation between properties. But if you average the AGN properties over an enough wide time scale, basically you are probing the same time scales between AGN and galaxies, and so these models also predict, and observation confirms, that there is a very tight correlation between AGN activity and star formation rate. And so they are basically fed by the same gas in a broad sense. And so to summarize, I hope to convince you that black holes play a very important role in shaping these properties of galaxies. And according to the most recent results, I mean, major measures don't play a significant role in shaping the evolution of galaxies. The scenario is much less violent than thought before, because probably is the stochastic falling of gas clouds onto the black hole which triggers the black hole, not violent interactions between galaxies, because they are very unlikely compared to observations. So the Edge-galaxy connection is now pushes for the coevolution between AGN and galaxies, where the star formation rate and the AGN accretion rate correlate, even if the detailed mechanisms that trigger both mechanisms, both components, are still poorly constrained. And this lack of correlation for individual galaxies is actually well explained by different variability time scales. And I will finish here. If you have any question, I'll be glad to answer. Thank you very much for your attention.
Any questions for Ivan? I'd like to know, how do you compare the time of the AGN and the universe? Because the different solutions of the Einstein equation.
Well, good question. I mean, typically there are simulations there are attempts to predict the evolution of the AGN, which is typically the time scales are from hours to mega-year, typically. While the galaxy emission is much more stable in time. I mean, the galaxy evolves on longer time scales, typically on at least 10 or 100 mega-year. So in this case, you would expect that the AGN could change very rapidly, the light cube, let's say, compared to the galaxy, and this would explain the lack of correlation. But I don't know how to connect it to the solution of the Einstein equations.
No, because you. The point is that you are using the black hole solution, let us say, to calculate time for AGN, but the time of the black hole solution is different from the time, the convolution time of the universe. How to pass from one time to the other time. To say that this is the time that we feel that the AGN is formed.
Well, you measure the distance. You measure the distance of the AGN, which tells you also how much in the past you are looking at this AGN. So
to measure the distance, you are using a cosmological model.
Yes, you are using a cosmological model to turn, yes, exactly, yes, the standard model.
Any other question?
I have one. So what about the future of the relation AGN is the formation rate? I mean, after Herschel, what's the
next step?
What's next?
Yes, and now, well, people have been investigating also the detailed mechanisms to explain this overall correlation that you see, because, as I mentioned, this is not the correlation for individual galaxies. But now people, you need really higher resolution to really sample the innermost part of galaxies and pick up the AGN emission. The galaxies are very, very distant from us. This kind of work can be done very, very well in the nearby universe, where the angular size of galaxies is enough large. So now we are waiting for new telescopes in different wavelengths, of course. The extremely large telescope, ALMA, that is already working. And the next step is already to combine a panchromatic view, but with new generation telescopes, both space-based and ground-based.
Okay. Well, let's thank you then again.
Thank you.
Move to the next presentation. By Ekaterina Karukas, who will tell us about modeling the mass distribution in the spiral galaxy NGC 3190.
So, good afternoon, everybody. I'm going to speak. I'm a PhD student at CISA, and this work was done under the supervision of Paolo Saluce. And the topic is modeling the mass distribution in the spiral galaxy NGC 3198. So, what about I'm going to speak? Firstly, I would like to stress what was the motivation to start to work with rotation curves of galaxies. Because rotation curves in spiral galaxies, and actually not just in spiral galaxies, and also other type of galaxies, provide convincing evidence of the dark matter existence. Then why we choose this particular galaxy? Just because the rotation curve of this galaxy can be considered as one of the most extended. And it is, of course, better to use a galaxy for which we have very good data. And then the main goal of this work is to examine the dark matter content of this galaxy. So the outline of my talk will be, firstly I will speak about the place of dark matter in the universe. Then I will give you historical information about possible evidences of the dark matter existence. And then I will move to the part which calls mass modeling, and I will speak about hollow-gas gas bulk decomposition. I will give you two dark matter profiles. It is Navarro-Frank-White profile and Burkert profile, and results. So, firstly, what is the place of dark matter in the universe? So we know from the Winkelson micro-anisotropy probe or from Planck that the contribution to the energy density of the universe. So, and we know that the baryonic ordinary matter contributes just 4.6% to the total energy density of the universe. Then there is dark energy, which contributes most of the dark energy, energy density. And there is dark matter, about what I'm going to speak. And we also can write down this relation between the energy density of dark matter and energy density of baryons ordinary matter, which is around 5. And surprisingly for everyone, that from cosmology and astronomy, we understand that the most energy density of the universe is of an unknown form. So, and I'm going to speak about dark matter from astrophysical point of view. So there are several evidences of the dark matter existence, and I will speak about two of them. In 1933, by Zwicky was discovered that in the Coma cluster, some of galaxies have unexpectedly large velocity dispersion. And then he applied the Weyl theorem in order to calculate the total mass of this cluster. And he understood that the total mass, the virial mass of the cluster, much larger than one which we can estimate from light, which comes from galaxies and of this cluster. And he concluded that there should be some great amount of unseen matter. Then later in 1970s, by Rubin and Ford, was first discovery of dark matter by using rotation curves of the Andromeda galaxy. And what one I will show you this picture, which is this is the galaxy about which I'm going to speak, NGC 3198. It is a spiral galaxy. And the rotation curve of galaxies usually measured by looking at stars and calculating the circular velocity of stars and different galactocentric distance, or using stars or using gas, which is rotating around the central part of the galaxy. And so one will expect that from, as an analogy of solar system, that the velocity of stars or the gas will be, so the gravitational potential of the galaxy is one which is produced by the central point mass. And so in the absence of other forces than gravitational, we will expect the circular velocity is proportional to the 1 over square root of galactocentric distance. And this is which describes this red line, which calls for obvious reason Keplerian decline. While they observed something which is more or less flat. So, and they concluded that there should be great amount of unseen matter, which is distributed in more or less spherical symmetric form, and they call it dark matter. Then, just in order to explain better, to have better imagination what about we're speaking, I give you this picture, which is again, this is the NGC 3198 spiral galaxy, and this circle is how we can imagine the dark matter halo. And the distance to this galaxy is around 10 megaparsec. This is absolute big band magnitude, which can be translated to a luminosity. And this is so-called inclination angle, which tells us how we see a galaxy, the position of a galaxy. So here I show you just several links on the papers where was described previous kinematical investigation of NGC 3198. As you can see in the different observations, like in the optical and in 21 centimeters, where in the optical we observe the rotations of the motions of stars, and in 21 centimeter it is gas. And this analysis is based on H1 observations, which was published in this paper. And so how we model, so we know we can measure the rotation curve of a galaxy. And we would like to get the information from this rotation curve. And that's why we do mass modeling. So, so in order to know the contribution of luminous matter and this unseen dark matter to this rotation curve, we model it in terms of different components of a galaxy. So there is the stellar disk bulge, which is the central part of a galaxy, which is populated by old stars, while stellar disk populated by young stars. And there is the gaseous disk, and then there is a dark matter halo. In this particular, so we can divide into luminous matter and dark matter. And in this particular case, from observations, we can exclude the central part just because it is very small, and we include it in the stellar disk. So you will see later from the rotation curve. It will be more understandable. And now I go to the part of how we model. We can measure this, we can measure this, but then we don't know anything about dark matter, and we should use some density profile. So, in fact, the first dark matter density profile, which I will describe it, is was proposed by Bunker in 1995. It is an empirical law which was taken from observations, which is based on observations. And here you can see how it can be reproduced, where rho 0 is the central density and R core is the core radius. And in our future fitting, because we will do fit to the rotation curve, these are three parameters. Then there is the second dark matter density profile, about which I'm going to speak. It is Navarro-Frank-White profile proposed by Navarro-Frank and White in 1996, and it is based on cosmological simulations of galaxy formations in cold dark matter scenario. Here is how we can reproduce this dark matter density profile, where rho s and rs are characteristic density and scale radius of the distribution. And in this case, we would like to a bit rewrite this density profile in terms of other parameters, which is one of them is the core radius, concentration parameter, sorry, which is the ratio between virial radius and scale radius, and the virial mass, which is reproduced by this expression where the number 100 means that we define the area where the density is 100 times more than the critical density of the universe. And we can do it. And at the end, we see that these relations here, and then we put it in the density distribution, and we model this in terms of two parameters, virial mass and the concentration parameter. While also we can describe, can get this relation from simulations, the relation between the concentration parameter and virial mass. You will understand later why I put it here. And so this is the results of mass modeling. So we, where on this picture you see that this is the rotation curve for the gaseous disk, this is the rotation curve for the stellar disk. So as you can see, there are two peaks, which one reproduce the central part of the galaxy, which is bulge, and then the green line shows the dark halo contribution to the circular velocity, to the total circular velocity, and then we sum them, and we have this red line which reproduce some of these three different rotation curves, and as we do fit. This is our three parameters. And as we can see, in this case, fit is quite good. And this is our best fit parameters. And then we can also estimate some additional quantity. It is the mass of the stellar disk, dynamical mass, and virial mass and virial radius. So here I show just to have an idea. The 1 to 3 sigma confidence ellipses for some parameters. This is mass to light ratio for the stellar disk, core radius, and so on. This is the case of the Burger profile. Then we move to the case of Navarro-Frank-White profile, where it is the same. The gaseous disk, the stellar disk, the dark halo, and the red one, it is the sun. As we can see as well, the fit is good. But in this case, for the scale radius and characteristic density, we have unphysical values, which is too small density and too big radius, which is unphysical. And also another point that in this case we can estimate the concentration parameter and compare with the result which comes from cosmological simulations for this virial mass. And we see that it is different, which can tell us that Navarro-Frank-White in this case doesn't work properly, as one will expect. And this is as well 1 to 3 sigma ellipses for different parameters. And in conclusions, I can say that the Burken dark halo profile fits the data very well, and at the end we have good quality fit, while the Navarro-Frank-White halo profile was found to have non-physical solutions for the parameters of the fit. Thank you.
Any question? So, are you planning on performing the same study also for other objects?
Yes, actually, there is.
And how many similar
Okay.
objects do we know? I mean, is this one a particular one for some reasons?
Yeah, this particular one for a reason that we have very extended rotation curve, so that we look very far away from the center, and it is, I mean, in optical rotation curves very well studied in the central part of the galaxy, but of course we would like to know what is going on the outer part, and this was the, for now, for today, is one of the most extended rotation curve. That's why we decided to study.
Okay. Well, if there are no other questions, let's thank you, Catalina, again. Okay, now we have Stefano Camera, who will tell us about cosmology on the largest scales with intensity mapping.
Thank you. Good morning. Thank the organizer for this opportunity. And well, this is an argument. This is a topic that I'm very keen to present because it's one of the main science cases for the new generation of cosmology experiments, like the European Space Agency Euclid satellite and the radio facility, the square kilometer array that will be built in the next 10 years or so. So my point is how the largest cosmological scales are important for doing cosmology and how we can access it, in particular with what is called intensity mapping. So the topic of my talk is it working? Well, okay, it's twofold. First of all, I want to convince you that these large cosmic scales are particularly interesting for cosmologists because they hide some effect that can tell us a wealth of information about the cosmological model. And then I want to show that though there are practical problems that make these scales very hard to access with conventional surveys and experiments, there are some possibility to study them for the new generation of experiments. And to do so, I will also present some results on forecasts regarding non-Gaussianity, which is one of the effects that shows up at these large scales. So let's start with the beginning and see why ultra-large scales are important for cosmology. So the point is that the statistical properties of the cosmic Gaussian structure are a rich source of information about the physics at the early universe, in particular those large scales, and then its subsequent evolution at the current state of the universe. So we can try to track back the evolution of the perturbation from now until the very beginning, basically. And so in particular, constraints on the properties of density fluctuation on these ultra-large scales in a redshift range between 1 and 5, more or less, so after what is called the reionization of the universe, can improve our understanding of the primordial universe itself. And this is because those large scales are mostly uncontaminated by the nonlinear growth of structure, which is something that it is hard to model out of cosmological simulations. And then also because those large scales are quite safe in terms of the effect of variance, so the feedback of variance, for example, in galaxies. Because these large scales are just dominated by gravity, and this is dark matter, and we know how dark matter works. So just to show you some example of the effect that show up in these large scales, I'm going to present 3 of them, and in particular, relativistic corrections that occur on cosmological observers. So let's suppose we observe some overdensity in the sky, so some galaxy overdensity compared to the background energy density of the universe. We do know that this overdensity at an observed redshift z and along the right side direction n can be decomposed into many terms. We have the usual term, the so-called local term, that is just the galaxy density perturbation itself, plus some other effect called Drexel space distortion. This comes from the fact that we are relating the 3-dimensional position of the galaxy by measuring its position in the sky as angles, and by measuring its radius in terms of redshift. But redshift is related to distance, but also to the peculiar velocities of the galaxy themselves inside the environment. So there is a transformation between the redshift space and the physical space, and this is what is called redshift space distortion. And then there are other terms like changes in volume that are entailed by these redshift perturbations. Then there are so-called weak lensing terms that are due to the fact that light rays coming from distant galaxies has to pass through all the distribution of matter in the universe before coming to us. And so they are scattered by lensing, gravitational lensing effect, and what we are seeing is not exactly the distribution of galaxies, the image that the photons coming from them at the beginning. And then there are other terms called time delay terms that account from the fact that by scattering over the last scale distribution of matter in the intervening matter in the universe, photons also get delayed by the potential wise of the last scale structure. And though most of these terms, the dominant terms, are Newtonian, so that can be worked out in the usual Newtonian approximation, there are pure relativistic corrections that are usually not accounted for. And so it will be very interesting to study the large scales, because those are the regime where these generativistic effects occur. And so that can tell us something about the goodness of generativity on cosmological scales. Because the other possibility is that the law of gravity that we know does not hold anymore on cosmological scales. And so this is what is called modified gravity. And modified gravity theories are basically attempts at solving the dark universe problems. So the fact that we have to postulate the existence of dark energy or dark matter, because we are observing something that does not fit to the usual paradigm that we know. And modified gravity theories are known to possibly exhibit large-scale distinctive signatures. And I'm not going into the details of these theories, but I just want to show that for a few viable or once viable modified gravity theories, we can see that. So these are power spectra, for example, the cosmic microwave background temperature anisotropy, and of the large-scale structural perturbation as a function of the angular or physical scales. So these are Fourier modes, basically. So this means that low multiples are related to large scales. So the lowest multiple, the larger the scale. And these black solid curves are what is expected from the London cosmological standard model. And the other curves are what is obtained in one of these modified gravity theories by varying some of the parameters of the theory. And you can see that in the regime where we are on small scales, these theories converge to what is the usual standard cosmological model, but on very large scales, they may exhibit very different deviation from general relativity. And finally, what I'm going to focus on is so-called primordial non-Gaussianity. So non-Gaussian initial fluctuation arise in several scenarios of inflation. This is basically the large-scale potential of the gravitational potential of the large-scale structure. And if we suppose that there is some degree of non-Gaussianity in the distribution, the statistical distribution of the cosmological perturbation in the very early universe, we can parameterize this deviation to Gaussianity from Gaussianity by a single parameter, which is this FNL. If we just expand this potential up to inner order. And even though this inflationary paradigms predict a small value of FNL, the evolution of perturbation after inflation can generate an FNL of all the unity models. So the method par excellence for constraining FNL has been so far measuring the higher order correlation function on the cosmic value background temperature and anisotropy power spectrum. And this is because if your statistical field, if your random field is Gaussian, there is no higher order correlation. All the information is contained within the power spectrum. But if there is some degree of non-Gaussianity, then you will be able to measure a non-zero bispectrum, for example. So this method has been used. The first measurement has been delivered by the maximum experiment, which constrained FNL to be less than 1,000. Then there have been improvements from other CMB experiments like Lagdunab that ended up with Planck experiment last year that states that FNL must be smaller than, say, 10 to be consistent with observations. However, there are non-Gaussian properties of initial fluctuation not only produce a non-zero higher order correlation function, but they can also lead to scale-dependent biasing and distinctive signatures on very large scales. The point is that if you have a biased tracer of the large scale structure of dark matter in the universe, this bias will be modified by some degree of non-Gaussianity that mixes small scale and large scale information. So what I'm going to show here is the ratio of the bias of halo in the large scale structure compared to the Gaussian case. So this one means that there is no non-Gaussianity. These points that you see comes from numerical simulations, and these curves are for different values of FNL. For example, these two curves are for plus or minus 500 and plus or minus 100. And this is the physical scale, so the Fourier modes in 3D, in 3D Fourier space. And you see that even large values of FNL, like 500 or 100, lead to deviation from Gaussianity at scales of basically 100 megaparsec. So this means that if Planck says that this value has to be smaller than 10, this deviation, if there are to be expected at very, very large scales, something like that. So we need to be able to access these scales. The possibility of using this biasing of the large scale structure as a proxy for non-Gaussianity has led to some results with GATS surveys, but there are no not competitive with Planck, for example. But why it is important to understand if there is some non-Gaussianity if it's so small? But the fact is that an accurate measurement of FNL and the shape of paranoidal non-Gaussianity will rule out all classes of inflationary models, because different kinds of non-Gaussianity are related to different inflationary models. I want to go to the details, but just to show it is important to understand the physics at the very, very early universe. So this is, I hope I have convinced you to some degree that there is something to be gained in studying the large scale structure, the ultra large scale structure of the universe for cosmology and for fundamental physics as well. And now I'm going to try to address why, how can we do that? So the problem is that the extremely large scales whereby these FNL effects of order 1, for example, occur, are extremely difficult to access. And for example, if the attempts at using the CMB are hampered by cosmic variance. Cosmic variance is just the fact that we have just one realization of the universe. And so if we want to probe very large distances, we have only a few possible combinations, whereas instead small scales are much more sampled in terms of statistics. And this is the power spectrum of the temperature and isotropies of the cosmic microwave background as a function of the multiple moment, or if you want, of the angular scale, which is written here. And you see the recent measurement of Planck, of the Planck satellite, which is very well measured on small scales. However, if you approach the larger scales, because of this fact, the points are much more scattered. And this band that you see here is basically what is due to cosmic variance. So if we want to probe something at this level, it will be very difficult because of cosmic variance itself. And this is why CMB has not brought other results than what we have. The other problem is, if you want to use the last case structure, is that there is practical problem with conventional galaxy surveys. For example, sensitivity at high redshift on the surveyed volume. And this is because even though we can span a large fraction of the sky with galaxy surveys, if we want to probe large scales, we need not only a large area, but we need a large volume. And it means that we have to go very deep in order to probe these transverse scales as well as the part. And this is the one of the most accurate measurements of the power spectrum of the cosmic last case structure as a function. This is the Fourier transform of the correlation function of galaxy clustering as a function of, again, of the physical scales. This is the physical multiples in Fourier transform. You see that this is what we expected from theory. These are the points. The agreement is remarkable. But theory predicts some turnaround here, but we don't have any point to probe this regime at the moment. So this is the problem that I was talking about for galaxy surveys. So how can we do that? And in particular to study non-Gaussianity. And the problem is that for realistic values of cosmological parameters, an error of FNL of order 1, so if you want to probe with an accuracy of 1, this parameter of FNL, this can be achieved only at it is out of the envelope calculation. It's not very difficult, but this can be achieved only at pretty high redshift, like 3.5. And I was saying that for galaxy survey, this is very hard to get the required sensitivity at such a large redshift and over a wide area of the sky. And this is because a galaxy survey is basically a threshold survey. So you need to count as enough photons, you have a sensitivity, you have to count enough photons for the source in order to detect and say, and see things. So this is why what is called intensity mapping is better for this purpose than galaxy survey. What is intensity mapping? Basically, instead of counting individual galaxies, so detecting them out of some threshold, intensity mapping is just integrating the beam, the integrated emission from many galaxies in one big pixel. In some sense, we are making a map of a temperature, like the cosmic microwave background, but with a map of temperature which is related to the contact in galaxies. And this is why we are using H1. H1 is in neutral hydrogen. We suppose that after ionization, most of the neutral hydrogen is contained in galaxies. So we make a map of the temperature of neutral hydrogen in the universe. And we relate this map, so the overdensity and underdensity of this map of temperature to the position of galaxies in the universe. And this is particularly useful for this large redshift because the H1 frequency, this is just gauged in our instrument, is directly related to the redshift because this frequency is just the wavelength of the neutral hydrogen redshifted according to the position that it has in the sky, so in the 3D dimension. So this is very useful and pretty simple to use as a method. And just the basics of this intensity mapping, if we assume that after ionization all this neutral hydrogen is contained in galaxies, then we can relate what is called the halo, thanks to what is called the halo model of structural formation. We can relate the distribution of halos in the universe to the distribution of neutral hydrogen in the universe within galaxies. Then when with some other assumption, for example, the line of sight scattering, etc., social phenomenon neglected, we can relate the H1 light radiation to the differential number count of halo objects. That means that basically we can build up what is the main ingredient that we need, so the bias of H1 compared to the last case structure. And for example, in the 2013, so last year, there has been the first measurement of this bias of H1 in the universe at a given redshift, 0.8. Particularly, what Spitzer et al. Measure is not that the bias itself, but the bias times the neutral hydrogen energy fraction in the universe. And we can use basically this measurement to tune the theory, so the theoretical calculation, in order to obtain the bias over a certain range of redshift. And this is what we obtain with the halo model. So this is the bias of neutral hydrogen as a function of the redshift. This is this black curve. And I'm going to show you here also the point where the neutral hydrogen is unbiased compared to the last case structure. So when the bias is 1, And this is particularly important because the theory of non-Gaussianity says that the non-Gaussian correction to the halo bias comes with a dependent on the bias minus 1. So it means that if the bias of the tracer that we are measuring is exactly equal to 1, we are not going to see any non-Gaussian effect, even there is some large value of FNL. This will be particularly important in what's more. And then we can build the power spectrum of neutral hydrogen as a function of scale and redshift, which is, as usual, the power spectrum of matter perturbation in the universe, weighted by the bias and by the temperature of the gas, because what we are observing is the temperature of the neutral hydrogen. And this is how it looks like. So again, this is the power spectrum as a function of the physical scale. These solid curves are just this P delta. So this is the matter power spectrum of the total matter in the universe as come from theory. And this dotted line are this matter power spectrum multiplied by the bias for one given value of FNL, just to show you some difference, and for two different values of for two different epochs. So this is Z redshift 0.4, this is redshift 2.5. If you remember this plot, you saw that before basically redshift 1, neutral hydrogen is under biased compared to the large scale structure, whereas it is biased after 1, and this is what you see here. So you see that the neutral hydrogen power spectrum at 0.4 is smaller than the matter power spectrum, whereas it's higher in the case of 2.5 as redshift. And this is the deviation due to the non-Gaussian bias. So this is the ingredient that I used to make this the forecast for this new generation of experiments. And this is what I'm going to show you at the moment. So just one single slide of review of what is the Fisher matrix approach that I used. So Fisher matrix are used to state the capabilities of a future experiments, for example, to measure some model parameters. And it comes from bias theory. And in the base approach, and under the assumption of a Gaussian likelihoods for the parameters of your model. So this is not the same Gaussianity that I was talking about before. This is just assuming that the likelihoods of the parameters of our model is Gaussian. The Fisher information matrix approximates the inverse of the covariance matrix of a given model parameter. So this means that if you want to measure, to know what is the capability of one survey to measure one parameter with a given uncertainty, we basically have the likelihood. We take the expected values of the Hessian of the likelihood. We have the Fisher matrix. We invert it, and the elements on the diagonal of this matrix are basically the variances of the model parameters. So by doing so, we can extract what is the forecast marginal error of one model parameter. And the model parameter that I'm interested in this case is just the FNL, the value of a non-Gaussian. So I will skip just this technical slide and just going to the result. So I calculated the forecast for model non-Gaussianity with the next generation of experiments, but before I would like to show you what's going on with some idealistic no-noise experiments. So just cosmic variant limited experiments. So what we did was to divide, take experiments that with the bandwidth covering 200 megahertz. So intensity mapping H1 experiment covering 200 megahertz, centered in different at different frequencies. That means centered at different redshift, in order to see what's going on and to understand what's the physics that is going on in these different cases. So we have these chunks, these boxes of universe whose radius is basically given by the fact that we are probing 200 megahertz in the distribution of neutral hydrogen in the universe, centered in different points. This is the volume of the universe that we are probing at different redshift. As obvious, the closer we are to now, the smaller is the volume that we can probe, because the transverse radiation is smaller. And as we go back and back in time, it's easier to probe larger volumes. So what we would expect, if I explain clearly enough, is that the larger the volume, the more information we have in non-Gaussian. And this is the expected error on FNL that we expect from this experiment. So as we were for two different values. Well, don't pay too much attention to this. These are two different values of the maximum angular wave number that we are plotting. So as expected, this is a curve that is going down almost monotonically. So the larger the volume, the more precise is the measurement of FNL. This is very good. There's something going on strange here. So we start with a bad measurement of FNL, so an error quite large on FNL. Then it goes down as the volume improves, which is good. And then there's something going on strange here because, again, the error starts being big. So what's the point there? The fact is that we have to remember what I was telling you about the bias. So when the bias is 1, we don't see any non-Gaussian effect. And that's why when we cross this divide of bias equals 1, again, the error starts increasing because they are not getting any confidence on the measurement of the FNL. Then, by passing this point, again, we have that at the redshift, as I was telling you before, of around 3.5, we can reach a very good measurement of FNL with an accuracy of almost 1. So this is just to understand what's going on, but unfortunately, there are no idealistic experiments. We have noise in our instruments. And so to understand this, we suppose the present or realistic purpose-built H1 experiment covering a bandwidth from 250 megahertz up to 1 gigahertz, which roughly corresponds to a redshift range between 0.5 and 4.5. And we divided this huge bandwidth into 75 redshift beams of with 10 megahertz. So slices of universe of with 10 megahertz between 0.5 and 4.5. So basically, we built up a power spectrum. Basically, this is the power spectrum I was talking to you about before, which is a tomographic power spectrum, divided into 75 by 75 bits. On the diagonal, there are the autocorrelation in the same redshift slice, and the off-diagonal terms refers to cross-correlation on different redshifts for this temperature of the H1. Unfortunately, this object here is quite nice, but it's quite difficult, cumbersome in terms of computational power to carry on. So we made some assumption, and we basically divided again this 20 by 20 chunks along the diagonal, assuming that cross-correlation amongst very distant redshift slices die away quite soon, so they are not correlated. Then we corrected for this superposition by adding other chunks in the middle, in order not to lose these cross-correlations here. And this is what we obtained as a result. So we took a dish survey. We need to understand what is the noise of such an experiment. Dish survey are just big parabolas. So the noise of such an experiment is basically given by the temperature of the system, the temperature of your antenna. The survey area, because the larger the area, the faster you have to scan the sky, and so you are spending less time in the same point. This is divided by the number of dishes, because the more dishes you have, the more precise is your measurement, the statistic that you have, the total time that you are spending in observing the sky, and the width of the redshift slice that you are observing. And this is what we obtained. So let me just spend a few minutes on this plot. This is these lines are ISO FNL contours in the plane of the survey area in square degrees, so very small survey and almost half-scale survey. And this is the total observation time, so the total time spending observing the sky times the number of dishes that we use. And these three panels refer to three different values of the maximum wave number, which is related to the dimension of the dish. So this is a small 5-meter dish. This is a medium-sized 15-meter dish. This is a very big 80-meter dish. And so we see that with a large enough time spending the observation, so the Planck constraint at the moment lies here, more or less around 10. And this means that with this intensity mapping experiment, even with not very large dishes, we can almost go to 1. This is the value of sigma FNL of 1 by if we are able to probe large enough area and spending some time or quite a lot, large number of dishes observing the sky. So what is the status of the art for present and future experiment? So most of these experiments are will be constructed in terms of the square kilometer array, the radio facility in Australia and South Africa. Some of these pathfinders for the square kilometer array are already under construction. One of these is Meerkat, which is 64 dishes of 13.5 meter diameter that will be upgraded to 190 additional 550 meter dishes for the first phase of the SKA. The only problem of this experiment is the minimum frequency is going to be quite large, 580 megahertz. So this means that related to the plot that I showed before, this will be a nice experiment to test this method, but it will give only with 580 megahertz, will give only an accuracy on FNL of order 10, which is comparable with that of Planck. So we can check, we can test, but it's not going to be competing with Planck. There are other experiments, for example, for the Australian SKA pathfinder, that will be large survey speeds and for new systems that are being built for that. But unfortunately, their high minimum frequencies will be unusable to probe large redshifts, and so the volumes that we need. However, the SKA phase 1 middle frequencies with its minimum frequency of 350 megahertz will be capable of pushing down Planck constraints. And in particular, with the full scale SKA, we'll be able to go up to this region in the plot that I showed before. And there's another possibility also that if you just build up some new dish survey from scratch, and you're supposed to have a very large number of pretty small dishes, just 4 meters, with a minimum frequency of around 4 megahertz, this will again be capable of measuring NFNL for the world. So the take-home message that I would like to leave is just the fact that ultra-large scales are very rich source of information for cosmology and for fundamental physics, because of the relativistic effect that is important for our understanding of the theory of gravity, modified gravity signatures, and inflationary physics, which is directly related to the fundamental physics in the universe. H1 intensity mapping experiments better suit the difficult task of accessing those large scales than usual galaxy surveys, and this is just because we are mapping a quite cheap and easy map of H1 temperature as much as CFD temperature and isotopies. And purpose-built H1 intensity mapping experiments can go below Planck, and there are many planet surveys that, or even cheaper settings that can do this in the near future. And that's all. Thank you.
Any question? I have a curiosity about the errors on the noiseless case, yes. So the idealistic case. So you show basically the errors on the sigma parameter.
Yes.
So is that parameter correlated? Have you investigated have you looked at the correlations of sigma with the other parameters of your models for the Fisher approach?
Of course. This is a very good question. Thank you. This is important because exactly we just carried on this example for just one single parameter, but there might be correlation with others. Luckily enough, it is known that non-Gaussianity is not going to affect much the information of the other parameters of our cosmological model. Although, if we include more parameters in our analysis, the constraints are going to get looser. However, it is also known that if we stay on pretty large scales, so this is why I was showing two different values of Lmax, on very large scales, the other parameters are not very degenerate with FNL. The only one or two parameters that might be degenerate with FNL on large scales are just the tilt of the power spectrum, because you are measuring that effect, and the overall amplitude. But the others, since are related, for example, to turnaround of the power spectrum or the baryon acoustic oscillation, occur on much smaller scales, and so they are not going to affect the measurement in FNL. But this is something that, of course, it is important. And this is why we wanted to see how it changes with the maximum Gregorian number in order not to stay in a safer regime and not to overstate the capability of observing.
Other questions? No? Well, let's thank Stefan again. We move to the last talk before lunch. By Claudio Mancuso, who will tell us about deep radio counts of star-forming galaxies.
Can you hear me? Good. Okay. First of all, thanks to the organizers to let me give this talk. I'm a PhD student here in CISA, and basically I work on models of galaxy formation and evolution. Well, as maybe some of you already know, there are different types of galaxies in the universe. Elliptical galaxies, spiral galaxies, and irregular galaxies with different populations of stars, and possibly different evolution and different formation. And how they are connected one to each other and how they form and they evolve is something which is actually not really clear nowadays. So basically what people do is to try to create some models, and with these models to predict some data, some observational data that then can be confirmed or not by actually observational experiment. And this is what I try to do in this in the first part of my PhD project. And so I try to make predictions for observational star-forming galaxies for the SKA, the square kilometer array. Let's start to see what's the square kilometer array. Actually, what it will be, since it will be built during these the next years, and it will be operative since 2020, the first phase. It will be the largest radio telescope, and it will have 1 square kilometer of area. That's where the name comes from. And it will be collocated in South Africa and Australia, and the capability that it will have is that it will cover huge areas of the sky at the same time. And of course, there are a lot of surveys which are planned for this experiment. But for my field of research, we are interested in these two, which are SKA1 mid, that covers these ranges of frequencies, and SKA1 surveys. These are all surveys on the continuum, so we are not looking at absorption or emission lines, we're just looking at the radio continuum. Okay, I told you that I work on star-forming galaxies, so what can SKA do for the star formation history? Well, he will detect very faint radio sources in the continuum with a high spatial resolution and large field of view, and most of all, it will be unaffected by dust extinction since it's in the radio band. And why is it important? Well, the star formation usually, of course, is connected with newborn stars that are that have a very high temperature, and so they emit basically in the ultraviolet. But the star formation usually is dust enshrouded. This means that the ultraviolet light is absorbed and re-emitted in the infrared. And this happens for most of the galaxies, with some exceptions. For example, at high redshift, that means very far in the universe, there are some young galaxies where the dust didn't have the time to form, and so basically we can still see these galaxies in the UV, or in the nearby universe at low redshift, where we have instead evolved galaxies in which the amount of dust is little, let's say, is littler than at high redshift, and so some UV photons can still escape inside the clouds and arrive to us. But also the radio emission is a tracer of star formation, in particular with two components, which are the synchrotron emission and the free emission. And the synchrotron emission is connected with the galactic magnetic fields and the electrons, and it occurs in supernovae shocks and pulsars, while the free emission occurs in H2 regions, which are the regions where the stars are formed. And there is a tight correlation between the luminosity, the radio luminosity, the free, and the synchrotron luminosity, and the star formation rate. So these are just two relations taken from the literature and that I use to implement the emission in my model. But what we need to do all these things is to know the star formation rate and how can we estimate it. Well, we have a model for it. We have a hybrid model that's been developed in the late 2004, and then that's been upgraded in 2006 up to 2014 by also this guy, which is a former student here in CISA. And this model is hybrid in the sense that we have two different approaches for spheroidal galaxies and lake-type galaxies. And the spheroidal galaxies are, let's say, modeled in a physical way, while the lake-type galaxies are modeled in a phenomenological way. And what I mean by this is that in the first case, we start modeling the dark matter halo, and then we go on until the star formation rate. While here, we take the observations and we go back to the star formation rate. And by the way, this model and these papers gave me the star formation rate functions in the ultraviolet, in the high Z galaxies, and in the infrared. And what was missing was the UV emission of late-type galaxies at low Z. And for that we used the phenomenological backward approach, and of course corrected for the dust extinction, and we improved it also looking at H-alpha observational data. H-alpha is another tracer of star formation, so just to be sure. And these are the results. So basically you can see, I mean, these are the star formation rate functions, so the number of galaxies with a certain star formation rate taken per slices of redshift, so at different time in the universe, different distances from us, let's say. And the thin solid curve is the UV emission, not corrected for dust extinction, while the dashed blue line is the UV emission corrected for dust extinction. So you can see that at low Z, basically, the UV corrected for dust extinction accounts also for the red data, which are infrared data. And these are the galaxies I was talking about before. So the galaxies that have a little amount, let's say, of dust, and so UV emission can still arrive until us. While if you go at higher redshift, you can see that this curve is not enough to account for these galaxies. So here, for these star formation rate functions. So here there is another population that comes out and is the one of the spheroidal galaxies. But basically, what I wanted to get home, to take home, is that infrared and UV star formation rate functions are complementary. So you can look it from here. This is the total star formation rate function, and it's made by summing up the UV and the infrared star formation rate function. So starting with this star formation rate function, I managed to obtain star formation rates that I put inside the relation I showed you before, and making some calculation that I'm not showing here to you because they're very boring, we managed to obtain number counts and number counts of galaxies. Of course, since we wanted to check if the relationship that I used were right or not, we made some observational, some check with some observational data. And we started from the, let's say, check with the free emission. Why? This is the spectral energy distribution of N82, I guess, if I remember well. And as you can see, this is the synchrotron, this is the free, and this is the dust contribution. So there is a region around 100 gigahertz where the free is dominating the contribution to the spectral energy distribution. And there are some new data in this range. They weren't available, let's say, before, from the South Pole telescope that has some observational data at high frequencies, so bigger than 95 gigahertz. So we made some checks, but unfortunately we find that something was wrong at 95 gigahertz, and we understood that basically because the estimated counts, so the one from the SPT, were estimated using a statistical approach. This means that the number of dusty galaxies was equiparated to the, let's say, probability that this coefficient, this alpha coefficient, was bigger than 1.5. Okay, let's say that the definition for a galaxy to be dusty is that this parameter is bigger than 1.5. So they didn't take all the galaxies with the parameter bigger than 1.5, they just take the probability. So if a galaxy had the probability, I don't know, 0.01 of being a dusty galaxy, they took 0.01 galaxy. And the problem is that at 95 gigahertz, there are many, many galaxies which are radio galaxies, so not dusty, and less galaxies which are instead dusty. So if you count 0.01 for a larger amount of galaxies, of course, the number counts in the end has some problems. So we assessed the data, and we collected data over the spectrum, over the spectral energy distribution, and we made the comparison with the spectral energy distribution predicted, and these are two results. So, of course, as you can see, this is the total, let's say, spectral energy distribution, and here there is no match with the data. So this is not a dusty galaxy, this is a radio galaxy. While, in this case, we have matched with the data, so this is a dusty galaxy. And I want to highlight that in this case, the alpha was equal to 1. So, I mean, it's good. The probability that alpha was bigger than 1.5 is equal to 1. So actually, it was bigger than 1.5. While here, it was 0.85. So in their estimation, they counted 0.85 galaxy in this case. But of course, this is not a dusty galaxy. And we found that only 4 galaxies were actually dusty galaxies. And so we make with this new assessment, we counted, let's say, the galaxies. We made the integral number count, and unfortunately, since we have only 4 galaxies, it's only 1 point. But so I mean, I know that statistically it's not so challenging, but this is what we have. But anyway, the match with the model is pretty good. And we made also another check at higher frequencies. And here we don't need to do the reassessment, simply because here the radio galaxies are much, much less than the dusty galaxies. So even if you count a bit more, I mean, statistically it's not a big problem. Then we concentrated on the predictions for the SKA, and we counted different contributions from different populations. So the AGN contribution, which is this one, the late-up galaxies contribution, which is this one, and the spheroidal and lens spheroidal contributions. And we summed them up, and we obtained this magenta curve, which is the estimated curve of the Euclidean number counts. And as you can see, I also overplotted here all the data which are available until now, and this, which is a probability distribution from Bergstrom et al. 2014. And what you can see is that basically the observational data right now just cover the AGN part. So where the AGN are basically dominating. Here we start to have the contribution of the star-forming galaxies, and in fact we have matched here. These data have been shown to be, let's say, too high by other authors already. We have the match also with the PD distribution, but what the SKA will be capable to do only with the phase 1 is to arrive until these 3 lines. These are just lines, let's say, flux limits for different circuits. So we can arrive to probe the star formation number counts up to here, which is, of course, a big challenge with respect to what we have right now. We also made other predictions at other frequencies, just because they were recasted, let's say, by the SKA community. And as you can see, also here, I mean, here, the observational data are even worse. Look, for example, here. Here we have only AGNs, while we want to probe this part. And the SKA will be capable to do it. We also produced some redshift distributions. In this way, we count how many galaxies we will have, or we predict to have, for the different populations, at per slices of redshift, let's say. So if you go, I don't know, at redshift 3, you will find this amount of galaxies. And what comes out from this is that, first of all, we will probe, okay, these 3 panels are just different flux limits for the different services that are predicted to be done with SKA1. And basically what comes out is that we will arrive to count let's say, a countable amount of galaxies, even at very high redshift. So we will arrive to probe reionization, because we can go up to redshift equal to 9, 10, and still count some galaxies. And another thing that comes out are the strongly lensed galaxies, the green curve, which are indeed a countable fraction of the total one. So again, they will be observable. And here there is another issue that opens because, of course, in order to understand which are the different, let's say, population, you need also to know the redshift, and this is another issue because we need some synergies with, for example, EELT or JWST to understand the photometric redshift of, the photometric redshift of these objects. Now, all this work, but is it really worthy to use SKA to trace the star formation? Yes, it is. And I'm showing you why. Okay, here there are the star formation rate limits as a function of redshift of different experiments of Herschel, for example, which is the, let's say, best device we had until now to plot star formation. And these are the limits. So it will arrive until here, while the SKA will improve by a factor of 2 the limit of star formation rate that can be achievable. And of course, the best star formation tracer is still the UV emission. This is an average from observational data. But the point is that, as I told you before, UV emission is available only for a little amount, let's say, of galaxies. And so, okay, it's good, but we can't use it for all of them. And this just to show you which, let's say, portion of the star formation rate history SKA will be able to address. So the SKA will be able to address this region where you can see we have here a completely lack of data. These are the Herschel data. And moreover, these two regions are very important in order to understand and to probe the star formation rate history. So in conclusion, what I did in this first year of PhD is that is to work out some predictions for the SKA and also its precursors. I didn't show it just because it's a matter of time, but we have also predictions for precursors. It's just a matter of changing the flux limit. And we did it both in counts and redshift distributions. We have it for different population of star-forming galaxies, both normal, late type, and also protospheroidal and mass spheroids. And we put inside the star formation of the moderate to low redshift late type galaxies. So we have a complete sample of star formation rate. And moreover, we tested the star formation rate relation with the radio emission. They work pretty well. And of course, we are waiting for the SKA because we need information not affected by dust. And the SKA will be able to do much better than Herschel, and so we're waiting for it. That's it.
Any question for Claudia?
I have a question.
Go.
How important is the radio emission for understanding how the stars are forming? I mean, how much are young stars emitting in the radio? Because what we are generally told in astrophysics courses is that the important part is near infrared.
That's right. That's right. The point is, it's not an issue of fraction of how much do they emit. The problem is that in order to understand the dust emission and the infrared emission, you also need, since basically infrared emission is just a reprocessing of the UV emitted light, you need to have a good model to, let's say, tell how the dust absorbs the UV light. While and then there are these issues. So you have to use UV for some galaxies, infrared for others. Some are more absorbed. In some galaxies, dust is thicker, so it absorbs more. It absorbs more. In other, it's less thick, so it absorbs less. And so it's not an easy issue. While the good point of the radio is that it doesn't affect it. So basically, you really get what is emitted. That's why we try to concentrate on the radio.
The intensity is lower.
Yeah, yeah. And the good point, in fact, is that we will have this wonderful apparatus that will arrive until very faint fluxes. Because the problem until now was that the fluxes, I mean, there weren't experiments that could arrive until those fluxes. Well, now we can. So this is the point. Thanks.
Thank you.
Okay, so as a very unusual point, we finished in advance. I don't know if this ever happened to you in any other conference, but you are so sharp that we will finish in advance. So we can have 10 minutes of general discussion about this morning session. If someone has some interesting points that would like to discuss with the speakers. Even for example, I work on this that might be related with what you do. What do you think about this possibility? Might we figure out something together? So we can have some free discussion. And the reason for this is that lunch is in 10 minutes. So even if you go now, the tables are not reserved for us. So we must find a fruitful way to use this time. So I encourage someone to say something. Don't leave me here.
It's a general question for all the guys in the US that show something concerning astrophysics. What kind of measurements do you perform in order to take your dates? So, which sense, yes, which instruments do you use to search in the sky your signals in practice? For example, CCD cameras or PMT cubes or what kinds of sensors do you use?
For plant is kilometers. And radiometers, yeah, okay. But I mean, it's not for optical images, it's generally CCD. If I'm correct.
Basically, it depends on the instrument you use. So
Radio will be radiometer.
radio will be radiometer, yeah. Interferometer. So it depends on what you want to see. Mirrors, if you want to. I mean,
Mirror is the system for
yes,
reflecting the light. Okay. I mean, it depends on the apparatus, but it can be quite complex. You have a primary mirror, a secondary mirror, and then the light goes into your sensor that can be barometer, radiometer, CCD, or polarimeter,
spectrographs,
spectrograph.
whatever
Right.
you need. It depends on the analysis you want to do, and also the same telescope can have different instruments mounted on. So you can do with the same telescope, I don't know, polarimetry or spectrography or photometry, and it has a photometer, a spectrograph, and a polarimeter.
Then you will have filters based on the wavelength that you want to observe, or polarimetric filters to trace out what you're not interested in for that measurement. So if you want to know about one specific instrument that was mentioned, maybe we can be more, the speakers can be more thorough in answering you. But the images, the optical images are, the labo images are like CCD taken.
Mine is a very specific question. Maybe there are two. The first question is how can it's to astrophysical guys. How can you measure the mass of black hole? This is the first question. That's good to know, but I don't know how to do that. The second one, is there any model independent way to understand what what should be the mass of the hypothetical dark matter candidate in a model independent way, using maybe numbers you showed in your graphs, you know, the bigger mind. Your I mean in general. Using the bigger mass you showed, I didn't know. I didn't know. The first question is very easy, I expect an answer.
Black holes. Who wants to answer to black holes? Can you pass me?
Yes.
Okay, there are different ways to measure the mass of black hole. For instance, in our galaxy, there is a supermassive black hole, and it has been detected because you can see stars orbiting around nothing, basically. And from the kinematics of these orbits, you can infer the gravity, which is responsible for this kind of orbits. And you infer basically the mass of the black hole because you don't see anything there. And then you just constrain the fact that this is a black hole because it is denser than any other kind of objects. And another way is through kinematics of the gas. Basically, if you do
Of the gas.
Of the gas orbiting around the black hole, basically you can constrain from the kinematics of this gas, since the gravitational potential is very large. You expect this gas to rotate very, very fast. And so you expect, kind of profiles which are unambiguously due to black holes rather than any kind of morphology, galaxy, and so on. So basically, from galaxies, from the gas orbiting, for the same principle that I mentioned for the stars, basically you can infer the mass responsible for this kind of kinematics. But it is always an indirect evidence. And then there are other ways based on time delay between different measurements. It's a bit, I put in a slide a bit or some image because it would be easier in any case. We can discuss it later. Okay. Thank you.
Someone else wants to say something about network or ask something more about network. Okay, so before we stop this morning session, okay, for the lunch is at 0 floor, the canteen, but you can go down and you will find it. There will be a sheet on which to sign next to your name, and except for Sister People, unfortunately, you will have to pay lunch for the day. You sign next to your name, and the lunch is included in the meeting. You will be allowed to take, if you want, half portion of first dish, half portion of main dish, side dish, thank you. And that will be and also pudding. Oh, pudding.
Or fruit.
Or fruit.
Or cake.
Or if you're lucky enough to have the cake, but
I don't suggest them.
I don't want to give false hopes.
Moreover, we don't suggest cake.
Exactly. No, cakes are not recommended. No. This is friendly advice. Okay, so we will start again at 2:30 with the last talk of physics and cosmology and the poster session. So poster presenters will be told hopefully right after lunch, which will be the exact order for them to present. So if you have a poster, please come to us immediately 5 minutes before the start of the session. We will be here in the room. This room will be locked, so you can leave everything inside here, because we will have the key and no one will be allowed to come in unless they are very expertise. So I think you can abandon any worry. And so see you in an hour sharp here. Let's thank again the speakers of this morning. with